Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about sparse regression, which is very useful in situations where we have many features, but we suspect that only a subset of those features are relevant to our quantity of interest that we want to estimate. We will see that L1 norm regularization, also known as the Lasso, I always say Lasso, although I guess you could also pronounce it Lasso, is extremely effective, and we will try to understand why. Let's get to it. We're going to talk about the Lasso and specifically about how to perform sparse regression via L1 norm regularization. Okay, so in case you don't remember, the regression problem is where we have this quantity that we call the response that we want to estimate from several features. So here we're going to have D features that we encode as the entries of a vector X. When we perform linear regression, we estimate the response as a linear combination of each feature that is weighted by a learned coefficient that we learn from data. We assume that the features and the response here are centered to have zero mean. That's why we don't have an intercept here. Okay? And here I'm representing the linear coefficients in vector form. If you look at this sum of weighted linear coefficients, it's the same as taking the inner product between the coefficient vector and the feature vector X. If we perform ordinary least squares estimation, this is equivalent to trying to approximate for our whole data set. So here we have n data points. And for each data point, we observe a response and an associated feature vector. We're trying to choose the beta for ordinary least squares such that over the whole training set, we have the minimum sum of squared errors between the observed response and the linear estimate. And again, here we don't have an additional additive constant in our model because we're assuming that everything is centered, which makes our life easier and is a common pre-processing step anyways. So let's take a look at how this works in our temperature prediction example that we already used in previous videos, where we're trying to estimate the temperature in Versailles, Kentucky. And I'm probably mispronouncing that for French people and also for people from Kentucky, so sorry. And we're trying to estimate the temperature there from the temperature at 133 other locations at the same time in the United States. If we use a lot of examples to fit a linear regression model, what we find is that the coefficients, which are represented here by these circles, and the bigger the circle, the bigger the coefficient, are dominated by three locations that are close to Versailles. So this star here tells you where Versailles is. And the contributions of other points that are further away are extremely small. This makes a lot of sense. This is a very reasonable estimator for the temperature in Versailles. You just do like a weighted average of the locations that are closer to that location. Of course, the method doesn't know about this. It learns this automatically when it has enough data. So here I'm showing you what happens for different numbers of training data n. When we have a lot of data, these three coefficients that are larger, so the y-axis here are the coefficients amplitudes, correspond to the three locations that are geographically meaningful. So that's great. But as we already discussed in our videos about overfitting, coefficient error, and rich regression, when we don't have enough data, that doesn't happen anymore. Why? Because there's noise amplification in the remaining coefficients that enable us to overfit this small training set, and then we don't see anymore. We don't obtain a good estimate of the coefficients anymore. So in sparse regression, our goal is to try to obtain a linear estimate that only depends on a small number of features, which for our weather example seems very reasonable because we expect the temperature to mostly depend on a few select locations. We want to identify a small subset of features that provide a good fit. So we have these two goals. One is we want to identify a small subset of features, but the other goal is also obtain a good fit to the data. Equivalently, we want to find a sparse vector of linear coefficients that provide a good fit. Sparse vector is a vector that has a lot of zeros. If you consider this inner product between the coefficient vector and the feature vector, which is the sum of the products of the corresponding entries, if many entries here are 0, then this is going to be equal to the sum of the weighted entries of X that correspond to non-zero entries of the coefficient vector. Okay, so here I'm calling that set of non-zero entries this weird kappa. I think it's a kappa, a big kappa. Okay, so maybe I kind of made too much, a big fuss out of something that is probably very simple. But my only point is that if we consider all of the features and we have a coefficient vector that corresponds to all of the features, if we want to perform sparse regression, we want to obtain a sparse coefficient vector that has a lot of zeros. And then the non-zeros will correspond to the features that we have selected within our linear model. We could think of applying rich regression to this problem because we saw that rich regression is good at controlling this noise amplification that occurs when you have small training sets. So we could just apply it and see if that yields a sparse model that only depends on a small number of features. Okay, equivalently, does this, if we minimize this cost function where we have the ordinary least squares term and also a term that penalizes the square amplitudes of each coefficient, does that lead to a coefficient vector that has a lot of zeros? Remember that this is the lambda here is a regularization parameter that determines how strong the regularization is. Well, let's do an experiment with some simulated data. Here, each of our examples depends on a single feature, and then there's some added noise. Okay? And we're going to produce a lot of examples like this where the noise is Gaussian. But we're also going to consider an additional feature. So just to be clear, this is the feature that corresponds to the response, but we also have an additional feature here that is spurious, that is not related to the response at all. And we're going to fit a model that has coefficients for both features. Of course, the coefficient corresponding to the true feature should be 1, and the coefficient corresponding to the spurious feature should be 0. The noise is IID with fixed variance. Now I'm going to show you what happens if you create many data sets like this of, I forget how many data points. Well, everything is centered to have 0 mean, so we don't have to worry about additive constants. I think these were 100 data points, but I'm not completely sure. You have that information in the book. The point is that I create many training sets with these characteristics, and then I look at the two coefficients. So remember that this is the true coefficient, and this is the coefficient corresponding to a true feature, and that's the coefficient corresponding to the spurious feature. And these are the true coefficients where the spurious feature is 0, and the coefficient corresponding to the spurious feature, is 0, and the coefficient corresponding to the true feature is 1, exactly what we want. What does rich regression do? It doesn't produce a solution that has where one of the coefficients is 0. It does not identify the correct coefficient. You could say, oh, but this is because you have small lambda, you see all of this noise amplification, so that's not too surprising. What happens if I make lambda smaller? It solves the noise amplification, but it does not yield sparse coefficients. If I increase lambda further, we bias the solutions towards 0, as we saw in the video on rich regression, but we never get sparse estimates. So rich regression does not work. What is going on? If you go back to the video on rich regression, we explained that rich regression does shrink the entries of the coefficients, which is exactly what you want. The problem is that it shrinks them in the basis of principal directions of the features, not in the standard basis. So this means that it will not produce a sparse solution, because the principal directions are not aligned. Like we're not going to get a principal direction that is just the first entry and then all zeros. So because of that, ridge regression coefficients are usually not sparse. So we cannot use ridge regression to solve this sparse regression problem. We want to identify a select number of important features. And the problem with ridge regression is that it uses the L2 norm. Here we're going to compare the properties of the L2 norm, which is the sum of the squared entries of a vector, and then we take the square root. We're going to compare it with the L1 norm, which is just the sum of the absolute values of the entries of a vector. Let's consider a very simple situation where we have a very dense vector where every entry is equal to 1 over square root of d, and we have a very sparse vector where only one entry is non-zero. If you realize, the L2 norm of these two vectors is the same. Why? Because here we're adding 1 over d, which is the square of the entries, d times, so this is equal to 1. And here we just have one entry, so immediately the sum of the squared values is equal to 1. Okay, so these two vectors have exactly the same L2 norm. Let's take a look at their L1 norm. So here for the L1 norm, we're adding 1 over square root of d times, so that's equal to square root of d. And for the sparse vector, we're just adding 1 time, so that's 1. So the L1 norm of the sparse vector is much, much smaller than the L1 norm of the dense vector. And you can also think of another example where you would have k entries that were non-zero, and then the remaining entries would be 0. If you do that, you can check. Okay, so here there's k entries that are non-zero, and then the remaining ones are all 0. You can check that the L2 norm by this same argument is still equal to 1, excuse me, and the L1 norm is equal to square root of k. So the smaller k is, the smaller the L1 norm. This shows you that sparser vectors that have more zeros, tend to have smaller L1 norms than dense vectors. And this is the motivation behind the lasso, which is an extremely popular way of obtaining sparse regression estimates, where we replace the L2 norm, which we use for ridge regression, by an L1 norm, and we still have a regularization parameter that determines the strength of this regularization term. So we have a term that is the ordinary least squares term that promotes good fit to the data, and we have this other term that promotes hopefully promotes sparse coefficient estimates. Does this actually work? Let's go to our simple example where we have one relevant feature and one spurious feature. Remember, relevant feature, spurious feature, because again, the response only depends on the true relevant feature. So we would like to obtain something like this, a coefficient where only the coefficient corresponding to the true feature is non-zero, but we have this noise, so it's not so obvious, and everything is centered to have 0. Oh, I thought this was good. Sometimes I try to guess what will appear in the slide, and I often get it wrong. So we had this like noise with fixed variance, and everything is centered to have 0 mean. Okay, so let's see what happens when we create many of these data sets and we produce the estimated coefficients using the lasso, where we're minimizing this cost function that has this L1 norm regularization term. So if the lambda is very small, nothing very special happens. We see the same thing. This is also what we see approximately for the ordinary least squares estimate. But when we increase lambda, boom, suddenly many of the coefficient estimates are exactly where we want them, because remember that this is the relevant coefficient, so we definitely want that to be non-zero, like in the true coefficients, and that is true for all of these guys. But we also want the coefficient corresponding to the spurious feature to be 0, and this is achieved by the regularization. Okay, there is a shrinking of the coefficients because of the noise are not going to be great. And because of the L1 norm regularization, you can see that they are biased towards 0, which is something that also happens with rich regression. But here they're biased in the right direction, where one of the entries set exactly to 0, which is exactly what we want. I'm saying exactly way too often here, because that reveals the true feature, which is the most relevant to the response. If we increase the lambda too much, we get a lot of bias towards 0, but still the same thing. We're identifying the true feature. This is a plot of the coefficients of the amplitude of both coefficients as a function of lambda. As we saw in the graphs, when lambda is close to 0, both are non-zero. So this is what happens with ordinary least squares. We don't identify the true feature. When the L1 norm regularization is strong enough, we have this sweet spot where we are identifying the true feature. We get increased shrinkage towards 0 of the true coefficient, and eventually, if lambda is too large, we just get the zero coefficients. So it works. Let's try to visualize a little bit why it works. So here we have the OLS cost function, where we see, and we're comparing it to the ground truth. So again, this is the coefficient corresponding to the true feature, and this is a coefficient corresponding to the spurious feature. So ideally, we would be on this line, which would indicate that the coefficient corresponding to a spurious feature is 0. But because of the noise, if you look at the least squares cost function, the minimum is away from that axis. Okay, the noise has moved the minimum of the OLS cost function there. Now I'm going to visualize a slice that is approximately here of this cost function. And what we see is that indeed the minimum is displaced from, this is just with respect to the second coefficient, okay? This is why I'm saying I'm looking at a slice like that. We're interested in what happens with respect to the second coefficient, so we fix the first coefficient, as we will see, we fix it to the coefficient of the lasso, but you would see very similar things no matter where you slice the function here. Because of the noise, we're shifted from the axis. So now let's take a look at the regularization term. This is the L1 norm regularization term, and the amplitude is determined by lambda. Here we have a medium lambda. You can, compute by yourself that the contour lines of the L1 norm look like that. These are the vectors that have L1 norm equal to 1, L1 norm equal to 2, etc. And now I'm going to cut this again like this. And when we do that, we see that the L1 norm has this kink at on the line where the spurious coefficient is 0. Of course, there's nothing special about the spurious coefficient. If we looked in this direction, we would again see like a kink where the first coefficient is 0. So again, nothing special. It's just this happens in the direction of every coefficient. But the important thing is that the regularization term is kind of doing what we want. At least on this line, which is kind of what we're interested in, it's doing what we want, right? It has like this kink at the point where the second coefficient is 0. And this is very important because when we combine it with the OLS cost function, that close to its minimum is quadratic, so it's less pointy than the linear regularization term. When we combine the quadratic and the linear regularization term close to where they are, close to the solution, the linear term is going to dominate. Okay, this spiky thing is going to dominate over the smoother quadratic term. And by the way, this is why you cannot use rich regression for this, because rich regression would also be smooth like that. When we combine both, the linear term is able to bring the solution to where we want it, on top of this line. Okay, so here again, this is the combination of the OLS cost function and the Lasso L1 norm regularization term. And what we see is that here, okay, in this line, let me draw a straight line for once. On this line, what we see is that the regularization term, this linear term, is able to bring the solution onto the axis where the spurious coefficient is 0. Okay, again, because the linear term dominates the quadratic term close to the solution. This is not achieved by the quadratic regularization term used in ridge regression. So hopefully that gives you some intuition about why the Lasso is able to produce sparse coefficient estimates. Now let's take a look at our real data example where we're estimating the temperature in Versailles from these 133 features. Remember that if we have a lot of data, then we see that there's 3 coefficients that are the biggest, and they're the ones corresponding to locations closest to Versailles, but we don't see this when we have a small number of data. Okay, when we have a small number of data, we see all of this noise, and that's what we want to solve. In this case, by promoting a sparse structure in our linear coefficients. This is what ridge regression does. Ridge regression actually works well for this problem. And I mean, it's a great method. We're not criticizing it here, but it definitely does not produce sparse solutions. So here, when the regularization parameter is kind of in the middle, it's not too small, which leads to just 0 coefficients. No, it's not too large, which leads to 0 coefficients, and not too small, which leads to just the ordinary least squares solution with all the noise amplification. In this sweet spot, it works well, and you kind of see that these coefficients are bigger, but many coefficients are non-zero. It does not perform this model selection. It doesn't select features by setting the other coefficients to 0. In contrast, if we apply the Lasso, and maybe I should have said that this is for a small data set that has just 200 examples, same as for the ridge regression example, what we observe is that, again, when the when the Lasso, in this case, this is the Lasso regularization parameter, is too large, we just get all zeros in the coefficient. And when it's too small, we get this noise amplification. In the middle, we get increasingly sparse, increasingly in this direction as we increase the regularization parameter, we get increasingly sparse models where the geographically meaningful coefficients are very large, and most of the other coefficients are exactly 0. So it does what we want. This avoids overfitting, and the way we see that is here we're plotting the training error and the test error for different values of the regularization parameter. So the training error is always going to be better the less regularization we apply, because we're essentially overfitting the training set, but we are fitting it better and better. But this results in overfitting. We don't generalize well to the test data, and that's why the test error increases. We get our best test performance exactly at this location where the estimates are sparse. So here, promoting sparsity is helping us to avoid overfitting and get a better estimate. In general, you have to decide on the regularization parameter using validation, where you have part of your training set data that is held out so that you can evaluate the performance for different values of the regularization parameter. If we do that, we do this for both ridge regression and for the Lasso, for L1 norm regularization. These are the parameter amplitudes that we obtain, the coefficient, I don't know why I said parameter there. Coefficients are parameters, right, of the linear model. So these are the coefficients that we obtain for ridge regression. And we do see that the geographically meaningful coefficients are prominent, so that's good. We also see that a lot of the others are non-zero. When we compare this to the estimates that we get after applying validation or cross-validation to select the regularization parameter of the Lasso, what we see is that many of those coefficients are now set exactly to 0. And because of that, these coefficients are more prominent. Okay, this kind of amplifies the relevant coefficients for the real data. And for this specific data set, this achieves better performance. So this is what OLS does. OLS gets great, like the training error. We're interested in this regime. Like when we have a lot of data, it doesn't matter. You should just use ordinary least squares. But if you don't have enough data, ordinary least squares overfits, very small training error, very large test error. When we apply ridge regression, actually we improve, well, we start not overfitting, so the training error is not as good, and this dramatically improves the test error. And when we enforce sparsity in this specific, I do want to emphasize this for this specific dataset where it seems that the response does depend mainly on a very small number of features, then sparse regression via the Lasso, via L1 norm regularization, further decreases the overfitting and further improves the test error, so we get better results. But again, this will depend on the actual real-world dataset that you are interested in. For some of them, it might make sense to enforce sparsity. For some of them, it might not. So what have we learned? We have learned that L1 norm regularization promotes sparsity very effectively. We've seen this both on simulated and real data. And if there are many features, sparse regression can be quite effective at avoiding overfitting. And also it provides you an interpretable model where many of the coefficients are zero. So you're precisely identifying the features that you are using for your estimate. And that's all I got. Thank you very much.